have something called the valence bond theory, and it says the orbitals can interact, right? They come close together, orbitals, okay, and they form a new orbital. So if you have a head-on collision using hydrogen as the simplest example, the two perfectly symmetrical spheres come together and overlap. Then you have this orbital, and it forms a sigma bond. So what happens is when it come together, it sticks around. You don't get, two solid ball here, but they overlap. So in the end, you have a volume that's seemingly smaller than the sum of these two. Do you see here? Because they overlap. They overlap means what? They share electrons. Electrons in the shared space are being hooked together. Now in this figure, we show the relative energy levels of two hydrogen atoms and the H2 molecule in hydrogen, right? So the H2 molecule, the hydrogen molecule, has 438 kilojoules per mole, less energy than the two separate entities of the hydrogen atom. You see, these are free hydrogen atoms, very high energy because they're not bonded yet, but when they form the bond with each other, they release this much energy. So conversely, when I want to break the bond of HH, I need to supply 436 kilojoules per mole to break it apart. Now in this figure, we have a plot of the energy versus the internuclear distance between the two hydrogen atoms. As we pull them apart, right, we are trying to break it. You see? So we have a energy that is 0. When you push them together, the orbitals can overlap. They share space, so we are forming a bond, so we will release energy, correct? Because we form a bond until this point of time where this is the optimum distance between the two nucleus. And that's how we form the strongest bond in hydrogen molecule. Now imagine if you push the orbitals even closer, what happens is the positively charged nucleus become too repulsive for each other, as well as the electron cloud. So these factors will, destabilize it because they tend to be more repulsive. It's like getting too personal into your personal space. When it's too close to you, you don't feel so comfortable. So too close, they repel and they will destroy the bond, and reaching very high energy, not going to happen that way, not stable. Now carbon comes from group 4. It has 4 valence electrons, 2s2, 2p2. The simplest kind of organic compound will be a methane, CH4. So all the 4 CH bonds in methane are completely identical, and they are spatially arranged such a way that they are all equal distance apart. So we call them a regular tetrahedron. Tetra for hedron means phase. We are dihedral. And the carbon will have an sp3 hybrid orbital. This may be a new term to you. What is a hybrid orbital? Like the word suggests, hybrid means what? It's the offspring. It is being generated. It's new. This means that I put in one of the s orbital and 3 of the p orbital. I mix them together, having the same amount of energy, same shape, so that they're all the same. And we need them to be the same because it's CH4. All the CH bonds are exactly identical. We are not giving any preferential treatment to one of them. So why would there be the carbon using its s orbital to form the s orbital of hydrogen, while the other CH bond comes from the formation of the s orbital of hydrogen and the p orbital of carbon? It doesn't make sense. So we have to make it fair, right? So that's why we have a theory called hybridized orbital. So that's why I'm saying that the 4 orbitals of the carbon will be mixed such a way that they have the same shape. We call it a hybridized sp3 orbital with the same energy, and they phase in a manner that is different from before, because before s orbital is spherical. But the p, y, x, z, they are all at right angle to each other. When you hybridize orbital, the orbital distance will be the same from each other, and the bond angle here will result in 109.5, and the bond length will be exactly identical, 109. Just think about it. If there's no hybridized orbital, the ss overlap will be shorter than a ps overlap. P orbital is larger, overlapping with s orbital, the bond should be a bit longer. But we know that all the CH bonds are the same strength in methane, so that means they must be the same orbital overlap. And the only way that can explain this is hybridized orbital. Let me have some tea first. Now the next molecule here called ethane, the second member of the alkane homologous series. How do we make the CC bond? So this carbon-carbon bond is formed by the s overlap of the two sp3 hybridized orbital of carbons. So for clarity, the smaller lobe of the sp3 hybrid orbital are not shown. You see, each carbon here are sp3 hybridized, so they'll take this, go closer, share it, and form this bond here, the sigma bond, the first covalent bond between any two elements. And tada! And all these bonds, orbitals, are being used to combine with the s orbital of hydrogen. Do you see? CH3, CH3. So these are just some representation of ethane. For the sp2 hybrid orbital, as you have known by now, that this comes from the insertion of one of the s orbital and two of the p orbital. Put them together, use a blender, mix them, giving off the same energy, same shape, and the distance and the angle between these three hybridized orbitals are exactly identical. And this is being illustrated by the structure of ethylene, also known as ethene, the first member of the alkene series here. You see that the p orbitals are all at right angle with each other, right angle, but after doing so, mixing with the p orbital, s orbital, you get the angle of 120 degrees, and it is trigonoplanar. So since we are only using two of the valence p orbitals, one of them is not being used. That means the last one is going to be perpendicular to this trigonal plane. Perpendicular, that's not used. Higher energy than the sp2 orbital. Right, so this is the side view. You see from the side here, this lobe in red and blue belongs to the unused p orbital that's not hybridized, whereas the green lobe is the hybridized sp2 orbital. Top view. Now if we are able to take these two carbons with the same hybridization and put them together, what happens is the p orbital, red overlaps with the red, blue overlaps with the blue. You have a pi bond, the sideways overlap of the p orbitals. That's how you form a pi bond. Of course, the sigma bond will be formed by the hybrid orbital. There's nothing new. So you see, these are the structures of the ethene, how it looks like in the orbital overlap. So many balls here, right? Sticks diagram. And here we show you the bond angle and the bond distance between the different atoms. Okay? You observe that because now there's more orbital overlap. So the carbon-carbon double bond right now will be shorter than the carbon-carbon single bond, because if you do not go closer together, how are you going to overlap the p orbitals? You have to be very close, you see, because they are perpendicular. Unlike just now where you have an ethane single bond, they inches to it this way, so ding, they just overlap. But here I would like to form the second bond, which is the pi bond, must be a sideways overlap. You see, imagine my hand, two p orbital. To overlap, you need to go closer, then you can overlap. But if it's a s orbital, ding, that's how easy it is. So now coming to the sp hybrid orbital, you will have known, throw in one of the s, one of the p, put them together, tada, two hybrid orbital, illustrated by the triple bond guy, acetylene or alkyne. So now we have two p orbital that's not used, and they are perpendicular again to the hybrid orbital. So the molecule of acetylene will be linear, 180 degrees. And this CC triple bond is even shorter than CC double bond, because now I'm forming two pi bonds, double overlap of the p orbital this way and this way. Have to be really close, if not you can't form the bond.